All right, I have 30 minutes above all, and I'll try to keep my talk presentation to this. But I also want to welcome everybody again to the webinar series. I see that there are a number of friends in the audience, and this is great. Thank you very much for being here, and I hope this will be some fun. And I know several of you contributed to all of this, especially FHI-aims beyond the MS1P team. And special thanks really go to the entire team in MS1P, Konstantin, Sebastian, James, and Andre, who really made this webinar happen and are also making the hands-on tutorial sessions happen tomorrow. So thank you very much. So I'm actually going to talk about work that we do with FHI-aims. And so the talk is titled Layered Hybrid Pervoskites, Organic-Inorganic Semiconductors from Spin-Orbit Coupled Hybrid DFT. I think you heard that my name is Volker Blum. I'm in mechanical engineering and material science and chemistry at Duke University in Durham, North Carolina. And I'm also one of the board members of MS1P who steer the FHI-aims code. And in fact, I think I did write the first line of FHI-aims many years ago and have been leading the code ever since. But it really is a community effort, as you know, because as I said, many of you in the audience know quite well who did the work. That is a lot of people. They will be shown towards the end of the talk, but really, I'm very grateful. So my agenda today is three things. I'm going to talk about FHI-aims a little bit, but there'll be a brief introduction before that, why FHI-aims and why this topic. And then one cornerstone that I'll be using for the talk is a periodic hybrid DFT. We need that in this case for energy band structures, things that require energy level alignment. And so this has been very good for us on the hybrid perovskite side. And in FHI-aims, as you may know, the hybrid density functional theory implementation has recently been pushed by Sebastian and several others beyond 10,000 atoms, and we're very proud of that on hardware that you can actually find. And then I'll come to the actual applications in layered perovskites. And I titled this structure, chirality, and spin. We can do much more. This is a very active field, as you know, but I only have so much time today. So thank you for this. So FHI-aims, I should say first, because that's one of the key topics. As you know, is an electronic structure code. When we started this, wanted to have something that was efficient, but also numerically precise and accurate in terms of the physical methods that we put in there. That was really the goal when we started, and there was one more goal that we were very interested in, which is to be able to handle both periodic systems and non-periodic systems on exactly equal footing. And so we did that using so-called numeric atom-centered basis functions. At this point, they're available in the code and they're easy to use, as you'll find out. But this is one of these basis functions. This is the atomic 4s function of copper that you see here. And it's localized, so it has a certain radius. And this type of basis functions is what enables us to do what we do in FHI-aims. Before I do that, let me get to this person. FHI-aims was founded in Berlin, but there was another person in Berlin, Gustav Rose, who was a mineralogist. And he's the first person who described the perovskite. So this image is from Wikipedia, and there's the 1839 publication by Rose that describes this mineral for the first time. Later, there was X-ray diffraction showing in detail how this is calcium titanate. This is made up of octahedra. They're connected over corners, and then there's a larger cation here in the center. And these materials, for many years, have been used as piezoelectrics, ferroelectrics, superconductors, magnetic oxides, and so on. And as you probably know, in 2009, things changed a little bit in the perovskite landscape. There are, of course, other perovskites too. So halide perovskites, in particular, have been around for quite a while. But a Japanese group showed in 2009 that you could use them as solar cell. They call it sensitizers, but really turned out it was the absorber. And so this paper here has been cited 22,000 times and counting since. And so methyl ammonium lead iodide, which was the initial material used here, suddenly became a superstar. And as a result, all sorts of other hybrid organic-inorganic perovskites that turned out to be useful semiconductors in their own right, tunable through incorporating less or more complex molecules, they also became stars. So this here is methyl ammonium lead iodide. You can see that the lead atoms, which are the gray atoms here, then the iodine atoms are coordinated octahedrally around them, and then there's an organic cation methyl ammonium, and you see a series of them here behind one another. That is the functionality. But you can make similar materials in other dimensionalities. For instance, you can have octahedra, but they don't have to be connected at every corner. So you can have a layered perovskite too, like this material here. So here is an inorganic lead bromide layer in this case. You have octahedra, and in between you have relatively complex molecules. And so the rationale behind this perovskite is that the organic functionality is optically active and the inorganic functionality is also optically active. So then you can play tricks like having excitons transfer from one component to the other and so on. But more generally, what you have here is the full flexibility of organic chemistry. So we have one component which is organic, and you can tailor that. And then you have the flexibility of the inorganic space that you can use, because lead bromide is not the only option. And so you can combine those two to make new functional materials, and that's what's kept a very large community going. So the person who made this particular material here is actually a close colleague to whom I owe most of what I know about perovskites, David Mitzi. And he made this material in 1999. And very often this is still the way in which we discover these materials. We find out if they can be made in the laboratory. This here is actually not an invention. So this is a three-dimensional crystal. It can be made. David made it. He did Laue diffraction, refined the coordinates. It's 400 atoms per unit cell if you don't have any disorder in the refinement. That's a serious endeavor, but we know that this material, as shown here, actually exists as a crystalline material. The alternative, of course, that we have is to try to computationally predict at least the properties of these materials. As you know, we have Schrödinger's equation, and that should give us, in principle, all of chemistry and a large part of physics. As Dirac said, if only we can implement it efficiently enough and accurately enough to solve for complex systems. And so in the perovskites in particular, you see that we have organic molecules. And so that means we have to deal with structural subtleties like the orientations of these tails back here. We have to, because the semiconductors deal with the alignment of energy levels. So if electrons, for instance, are lower energy on the organic, that's where the electrons will go. If electrons are lower energy on the inorganic, then they'll go to the inorganic. And that will change the properties of a semiconductor drastically. Similarly, it turns out you can break the symmetry. So you can make these materials, for example, with chiral molecules that breaks inversion symmetry. And suddenly you'll get energy bands that have a defined spin expectation value. And so you can explore spin properties and also spin transport properties in the materials. Phonons, of course, play a major role. And so they can also be incorporated. There's the question of optical emission properties in general, or absorption properties that you might want to choose, and so on. All of this we'd like to simulate in principle. And so, as I said, we, and in particular here at Duke, our group has been quite happy that we had FHI-aims, the code to do this, because it enables a lot of things. So in general, however, this is a general purpose electronic structure code. The vision we had at the outset was to be able to simulate real and complex materials and their properties, and we did not want any a priori precision or accuracy limits in the code. And that's what we've been pushing for ever since. And I think we've come quite a long way, especially in the realm of the things we're talking about today, which is hybrid functionals and dispersion correction. The premise was that we wanted an all-electron code, and that is because we knew this could be done, and particularly with numeric atom-centered basis functions, which are the numerical discretization underneath. We knew that this should be possible with high precision, but without losing efficiency. We wanted non-periodic and periodic systems on equal footing, and we do need computers. So we are quite grateful to the people who make working computers because we use them. And so we want to be able to scale to large systems. Often the reasonable limit for first principles that we find is thousands or maybe 10,000 of atoms. But that is what we actually need, it turns out. We did not want any precision limitations to be imposed at the outset. And we wanted to scale to scale seamlessly from something that is my laptop. And in fact, I can run a hybrid DFT calculation on my laptop. So not for 400 atoms, up to massively parallel computers, and also new high performance computing architectures, which all of the major computer vendors are now pushing in terms of exascale architectures. And so this is, of course, always ongoing work, but that's what we wanted. And then the main production method that I'll be talking about today is density functional theory, which still seems to be the sweet spot for many direct simulations quantum mechanically, especially in material science. But FHI-aims also has a reasonably large investment in correlated methods for many years, almost 20 now, in terms of the random phase approximation, GW, coupled clusters in there via an interface to the CC4S infrastructure, and many others. And again, the critical choice is that we'd like to use numeric atom-centered basis functions because of their precision. And none of this would work if we didn't have a community. So FHI-aims is really intentionally a community-based code. It is steered at this point by MS1P, which is a nonprofit based in Berlin. The purpose of this nonprofit is really basic science. So as you know, we license the code to industry, and that has been immensely successful, but I hope for both sides, because this has enabled us to make the code better for all people involved, including our industry partners, but also the entire academic community. And without the work of the academic community that actually contributed all of the features in FHI-aims, we would be nowhere really. This is very important. Thank you for everything you've done. All right. So as I said, the central decision on numeric atom-centered basis sets. This is the same picture that you saw on the first slide of one of these radial functions. The key point is that in any quantum mechanics, we started with a basis set expansion for the wave functions and then also for the densities and all other observables. And that is usually some linear combination of some functions. And in our case, these functions look like this. They are an angular momentum function. And then the radial part is flexible and can be tabulated as a spline. And that's important because that spline is flexible in its shape. And so this enables us to get, for instance, these wiggles back here near the nucleus, right, which are critical to get the all-electron component numerically controlled. And then we can use more functions than just single functions for every orbital. As you know, we can create basis sets. And that gives us the flexibility to converge chemically bonded systems. The flexible shape of the basis functions is one advantage. The next advantage is that these are naturally all-electron functions because you can mimic, not mimic, but actually capture the behavior at the nucleus accurately. They're also strictly localizable. So you can use, for instance, a Schrödinger equation with a cutoff potential to bring them down to zero smoothly at a chosen distance. And that does not have to be small. That can be 4, 5, 6 angstroms away from an atom. But the key point is that there it ends. And so for a large system, this means that you can decouple different regions in space, and almost all operations can be written to scale as linear scaling with system size, except for the eigenvalue problem, which is a separate problem of its own that we've worked on for many years to make that scale efficiently, and that we have, as you see. And then finally, this wouldn't work if we didn't actually have collections of functions that you can plug in. And so I spent some years with several others trying to create basis sets that work. So we have compact basis sets for numerically converged results, and they even exist in a hierarchy of basis sets and numerical settings like intermediate tight, really tight, that you can just drop into the code, and that will work for you at the level of precision that you would like. And that basis set library, especially for density functional theory, gets from fast qualitative convergence, if you want to do something rapid in terms of screening, to milli-electron volt per atom converged total energy, if you want to, and that's been extremely reliable for us over the years. So we're quite happy with that. We're not the only ones who tested this. We did a host of testing over the years, as you probably know. I continue to show this one, which is the delta test that was put together by Kurt Lejagueret and Stéphane Cottenier in 2016 for a science paper called Reproducibility and Density Functional Calculations of Solids. That compared the numerical precision of different density functional codes for something that should have been captured equally by all of them. In this case, energy versus volume curves by different codes, different parameterizations of the underlying mass for 71 elemental solids. That's probably the biggest thing that actually they got almost all elements that could be done reasonably between the codes together and got data. And so then you can compare. And so if you look at the all-electron codes, including FHI-aims, they're very close to each other. And we were quite happy about this because we did not have to change our basic settings for this. We actually got this with these settings out of the box. So this really does work. But what we've also worked on is scalability. So for a long time, we've achieved highly efficient and scalable semi-local density functional theory. So PDE, local density approximation, other generalized gradient functionals, and so on. And so out of the many benchmarks we did, I chose here the one done by Victor Yu in the context of GPU work in FHI-aims in 2021. which focused on a heavy element system, copper barium tin sulfide. So this is a semiconductor that may have its own uses in photovoltaics. But the key point is that we had a 3,000 atom model here to show that we can actually scale for heavy atoms and heavy elements, not just for some toy system. And this is a system that we worked on for a long time in my group as well, which is monolayer graphene on a silicon carbide slab. So this is a slightly different system, slightly different elements, but the key point is that we wanted to demonstrate that the scales. So on a traditional CPU-based computer, this is the Cori supercomputer, which existed at NERSC, National Energy Research Supercomputing Center at the time. You see that basically the total time for this copper barium tin sulfide, the blue line here, scales pretty well, not quite ideal scaling, but this is from 40 to 80 nodes. So this is between about 1,000 and 2,000 processor cores. And the blue line here, the dashed line, is marked alpha. This is the eigenvalue solver library that I won't have much time to talk about, but the massively parallel eigensolver library alpha, and the LC infrastructure, which connects this and other solvers to FHI-aims and actually various other codes, and all of this is open source. And the electronic structure library of the SICAM Center have been critical for us to achieve what we could do. And you can see that if you go to Summit, which is a 3-exascale architecture and GPU-based, you get the same thing, except you can do that on 4 nodes here, and you get slightly better scaling out for these particular test cases. So we are quite proud of this. And in particular, this paper here was about the alpha eigensolver, and the alpha eigensolver time came down quite a lot through CPUs, and that's been continuing since 2021. Second, we have the hybrid functionals, and I mentioned that in the beginning already. This paper appeared very recently. This really is hard work by at least 10 people, actually more, for 15 years, I would say. And this paper in particular is worked for 5 years by the lead authors here, trying to use practical paradigms for programming like the MPI-3 standard, which allows you to do shared memory, but controlled inside the code. So the user doesn't have to worry about this control. The code will do this for you. That works quite well. Better load balancing, better limiting of memory for large systems, blocking to optimize on CPU architectures and so on. And so eventually through numerous optimization steps, this allows us to do something like a 3,000 atom hybrid perovskite calculation with spin-orbit coupling, with band structures on a real existing machine. So this is about 1,000 CPU cores on an Intel architecture, but this is a fairly standard setup, and that you can still get. And so this seems large, but you can see that the hybrid density functional here, which is in this case the HSE functional, takes about 300 seconds per iteration still. The eigenvalue solver actually also comes up alpha with about 70 seconds. But if you then contrast this to the other things in this image, suddenly the system doesn't seem so large anymore. There's a paracetamol crystal here, which is 10,000 atoms with somewhat more basic functions. And so it's a much larger system, and you can see that the scale also, this actually, in this case, the eigenvalue solver outdoes the hybrid density functional part. We can do the same thing with forces, so then the time goes up a little bit more because we have forces in the game, but that can be done. And then finally, because he could, Sebastian demonstrated that we can also do something. Well, this is 15,000 atoms, sorry, an ice crystal, and we can do something like 30,000 atoms in an ice crystal as well, which is then the largest system with hybrid functionals that we are aware of in a direct calculation that has been done. But it actually works, and so we're quite proud of this, and this works with reasonable reasonable effort compared to what possibly before, because we don't think this is possible. So that's the hybrid DFT part. There is the question of accuracy, right? And so it turns out that dispersion corrections, van der Waals interactions, are quite critical. And FHI-aims has a long history of including van der Waals interactions. The Tkachenko-Scheffler method in 2009 was our starting point here, which was implemented by Alex in FHI-aims. And that's carried for simpler systems that are not so finicky. My group, for instance, very well for many years. Alex went on to develop a many-body dispersion approach with his group, which then I think makes a real difference in molecular crystal structure prediction. So this is the paper that formalizes that approach. And the group went on to develop a so-called non-local version of the many-body dispersion that also covers systems where the density is not just weakly, but maybe strongly connected. So Jan Herman did this work in 2020. And then there's the group of Aaron Johnson co-workers who have implemented their exchange dipole moment method. It was developed by Aaron and Axel Becke back in 2007, also in FHI-aims. And this is also very promising together with certain hybrid functionals for dispersion interactions. But there are a variety of other dispersion interaction methods in the code that are available, including recently the D3, thanks to James Green, who connected to the open source library by Sebastian Ehlert and Stefan Grimme. And so this is growing, and this enables us to do calculations that capture both the short range accurately in terms of hybrid DFT and the long range dispersion interactions for these weakly bonded systems, where the weak bonding, however, is important. We can use this. So this is a hybrid perovskite, and this is an undergraduate student, Douglas Heine, who is now at the University of Michigan, who did the bulk of this work. We did a benchmark study of methyl ammonium lead iodide, this decomposition reaction here, because there's experimental reference data for this decomposition of the material into lead iodide, methylamine, and hydrogen iodide that measures the vapor pressure of a crystal in vacuum, essentially. And the experimental data are the points here. And to cut to the chase, we can do a computation using hybrid functionals, which are dispersion corrected for total energies, then do a vibrational correction using a generalized gradient approximation, PBE, to get free energies out. We can do the quasi-harmonic approximation in this case to get volume changes in. And for the gas phase species here, we can do traditional thermochemistry and use the ideal gas law to get the temperature pressure behavior right. And then finally, these molecules here will rotate at finite temperature. And so we need a configurational correction of the entropy for the rotor of methyl ammonium. But all this can be done if you put this together. So this yellow dashed line is probably the best one that we have. The yellow dashed line is really on top of the experiment, and that is, in my view, too good. But it actually seems to work. And so we can do thermochemistry for something as complex as hybrid perovskite. I'm getting back to this slide, which you've already seen, for the layered perovskite for the last, I think, given the starting point, I have about 8 minutes of the talk. And this just shows what we can do with a hybrid perovskite. As I said, these can be large systems, but they do need high precision because the bonding between the inorganic and the organic part, and also the bonding in the organic part, is quite subtle. And so our observables for this talk will mainly be high precision atomic structure, as well as total energies and energy differences, and then energy band structures that are calculated for large complex systems. And for this talk, it turns out that semi-local DFT, so PBE, with the Tkatchenko-Scheffler-van der Waals correction, has actually been good enough for the perovskite work that we've done. Although we know we could do better, right? We could use any of the other methods as well. This carried us quite far in comparison to X-ray diffraction structures in particular. And then for energy band structures to get energy levels right, we've actually been very successful, even for the very large systems, with hybrid density functional theory. I won't, but critically, we need to include relativistic effects, so spin-orbit coupling, and we do. I won't go much into detail about the validation, but we validated this indirectly using optical experimental data many times, and it seems that especially energy level band alignments between the materials seem to come out very reliably. But we can do this. So Yi Yao and Gabriel Cognate and also Sebastian Cocotte did this work a number of years ago. We were interested in doping of a particular layered perovskite. This is so-called phenethyl ammonium lead iodide. So for the purposes here, this is a layered perovskite, but it's a semiconductor. And one thing we were hoping for, see if we could get any electrons, free carriers, into the material by switching out a lead atom with an atom that's 1 proton heavier in the periodic table, so bismuth. That should bind an electron. And indeed, if you do a large enough supercell, 1500 atoms in this case, we can also go larger, as you saw earlier, and you run an HEC calculation with spin-orbit coupling, and there are no tricks here. This just worked, and you look at the orbital of where that individual extra electron on bismuth is. It's localized on the bismuth, which is the cyan atom here, and it's localized in the unit cell. And in the energy band structure, which we can also calculate, you see that this leads to a filled energy level in the 0 temperature limit, which is actually pretty much flat. And this means that for purposes of defect calculations, the supercell is large enough to decouple the defects. The conduction bands of the material are the green bands here. Unfortunately, this effect level is about 0.5 electron volts below the conduction band. So this is actually a relatively deep dopant, not a shallow dopant, and you have to put a lot of bismuth into the material to make a small difference. But nevertheless, we can do this type of calculation directly, and so the energy levels come out where they should be in what the experiment agreed with in this case.
Around 4 minutes left, Volker.
Yes. And one critical point is that with smaller supercells, we would not get the flat band. So this is the 1504 atom supercell again, that you saw on the previous slide. But if you did this with a supercell that also seems respectably large, like 376, or even the smallest one here, 188 atoms, you see that these bands are much more dispersive, and so they're not well separated, and you don't get the properties of effectively isolated effect. I mentioned that spin-orbit coupling matters. So this is the picture that we have. We could in principle do non-relativistic calculations, right? And this is the energy band structure that we get. If you incorporate scalar relativity, which is critical for anything, I think, in chemistry, also lighter elements, then you see that the energy bands shift, but they don't change really in character. And if you incorporate spin-orbit coupling finally, then you see that something qualitatively changes. These two levels here split as they should, and the energy band gap also changes. And so the conduction bands in particular are heavily affected. And we can do better. We have a quasi 4-component method implemented in the code that solves the Dirac equation. And you can see that for something as heavy as lead, there's a small difference in the band gap, but this is actually within the accuracy limits of hybrid functionals as well. And our scalar relativistic plus spin-orbit coupling approach has worked quite well over the years. We can do more. We can, for example, look at optical properties, and this is just a comparison of experimental versus computational optical properties of this phenethyl ammonium lead iodide. It's an anisotropic material, so it has optical properties that are different perpendicular versus parallel to the planes. We capture that in the calculations with the exception of the exciton. This is a peak for who knows this. This is an excitonic peak, and that is not within density functional theory, but it can be captured by our collaborator, Pete Sercel, who can use our band structures and subsequently parameterize something called multi-band effective mass theory, which is traditional semiconductor theory, and get this. And then finally, we can do things like organic-inorganic quantum wells. So we can, with our colleagues, study crystals that they can make in the laboratory, where these perovskite layers become thicker and also the molecules become larger. These are 9 materials that were made in the lab of Letian Du as single crystals. This is in itself a huge achievement. We can do calculations. What we can do in short is we can find out what kind of quantum well is this. So will the electrons be on the organic component or will they be in the inorganic component? Same for holes. You can play this with 4 different combinations, but this really determines the optical properties of the materials. So we can calculate band structures in very short and find out these energy level alignments, and they agree with the emission properties, and Letian and others then went on and showed that this can also be used as lasing materials. And then finally, I mentioned chirality and spin at the outset. So we've done quite a lot in this because you can put chiral materials in, and that will change the symmetry of the inorganic also, and so the electronic properties. Very quickly, this has been used in light emission. This has been used in even a diode that was made by our colleagues at National Renewable Energy Lab, and also in spin transport. So you can basically take a chiral perovskite layer, get spin up carriers, they go through just fine. Spin down carriers will be blocked. So these are actually spin filter materials as far as something called the chirally induced spin selectivity effect. And so this is quite exciting for the spintronics oriented community. And we can look at the chirality. We can go to our colleagues here, our experimental colleagues, David Mitzi, Manoj Jana, Rui Zhong did calculations. They did X-ray diffraction. They looked at hydrogen bonds, and they showed in detail how inversion symmetry breaking is conveyed to the inorganic layer. And in short, we can calculate energy band structures. What you see is that if the material was centrosymmetric, you would get 1 band. If you break the symmetry, you actually get 2 bands where the color indicates the spin character. So these energy bands suddenly have defined spin character. This is called Rashba or Dresselhaus splitting. And we see this kind of splitting here in the band structure that we calculate for the symmetry broken materials, and we can quantify this and do more analysis. And so this has been ongoing work in our group for many years. But I have to thank my group. So these are the people here at Duke that did a lot of the work over the years. So I mentioned many of them during the talk, and some of you are here. So thank you very much for this. In fact, William Hoon, I think, is also here, and his success is spin-orbit coupling method, which underpins pretty much everything that we do. This is great. We have lots of experimental collaborators on the perovskites, both NSF funded and Department of Energy funded, and without them, we would not have nearly had as much fun as I think we did by really getting electronic structure theory and experiment to be complementary and match. And then finally, and most importantly, these are the 190 names in the meantime that we have on the FHI-aims website. If you're not on there, you should tell us, because we want to put you on there, right, and more. This code would not exist if we hadn't had so many people put in ideas that we did not have, right, that were your ideas and that pushed the code into a certain directions. This has really been a lot of fun for many years. I hope it's going to be a lot of fun for many years to come, but thank you, because really without the underpinning of a broad academic community that works together on this, we would not be there. And so this is my summary slide. I think I talked about everything here, FHI-aims. I did want to emphasize the libraries that I only touched upon in the talk again, because without this open source ecosystem that we've tried to contribute to also for many years, but with whom we've worked also in terms of other codes, we would not be nearly as effective. So thank you very much for this. We try to give back in that area. We've made some key scalability improvements in the past few years that are highlighted in this talk, and then I applied this to layered perovskites. Thank you. Thank you again.
Thank you so much, Volker. Very nice talk. So now we have the Q&A session, which is open. Yeah, and I see some reactions already from the chat. And I want to introduce you to James Green, one of my colleagues, also working at MS1P, and he will take over the Q&A session. So James, please go ahead.
Yeah, thank you. So yeah, feel free to everybody type questions in the Q&A, or if it's too long to type, then you can also raise your hand and I can unmute you and you can ask the question live. So yeah, Volker, we do have one question in the Q&A at the moment. Do I understand correctly? You use PBE plus van der Waals correction to relax the structure, and then single shot HSE plus spin-orbit correction on top of the structure. Why is the van der Waals correction included for the HSE calculations? Oh, what? Sorry, why is not the van der Waals correction included for the HSE?
Yes, yeah. So this is a very good question, and the answer is, first of all, very simple, but it's a great question nevertheless, because it's a frequently asked one, and it's important to keep that in mind. I'm trying to keep my screen visible. I'm sorry, it blinked. So we can, of course, no problem include the van der Waals correction into HSE, but we use the HSE here for a different observable. So for the perovskites, we use PBE and a dispersion correction for the structure. The structure usually starts at the X-ray structure, but we get certain aspects better than the X-ray diffraction, for example, hydrogen bonds. So the DFT will actually correct artifacts of the X-ray structures for hydrogen bonds. And that's why we do this. And so for the structure optimization, absolutely we need a good density functional, and we use a Schenker-Scheffler correction in this case. But we could do better, and the reason we use PBE plus TS is because it's the most affordable method that we have, and it's worked for us for many years, but there's no problem doing more. Now in the energy band structures, we're calculating a different observable. We're calculating single particle-like energy levels and their energies. And in that case, the van der Waals correction could be included if we used a self-consistent van der Waals correction, but we use a non-self-consistent van der Waals correction in all of this, like practically everybody in the field does, because that appears to be good enough. So you calculate the energy self-consistently using the PBE or HSE functional, and then non-self-consistently you add the van der Waals. This means that the van der Waals correction in this application simply doesn't affect the energy levels. Contrary to spin-orbit coupling, which on the energy levels has a big effect. So in the total energies, that effect remains manageable. Yeah. But in the single particle levels, spin-orbit coupling really has to be included. And that's why spin-orbit coupling is critical for the energy band structures. Yeah.
Okay, I hope that answers thoroughly the question. I don't see any more in the chat at the moment. And no hands raised. Oh, wait, there we go. So one hand raised. I'll just allow you to talk, Batam. Okay, you should be able to mute. Yeah.
I just have a very simple question. These days, I am seeing people are like working on these all electron codes. So my question is like, can you give me, let's say, one example where some physical example, not something like in terms of numbers that, okay, this number is better than if I use all electron versus something like valence electron system. Any physical where I can intuitively understand, okay, these are really important to like these kind of codes where people have all electron incorporated into their calculations.
Well, you can look at the benchmarking literature, right? In the case of the delta test, there were numerous pseudopotentials that were simply wrong in the literature. And yes, you can probably for every particle parameterize a pseudopotential, but I had this experience early in my career that I had to test the pseudopotentials, and if I didn't test, I would run into errors. I'm sorry about this, but this is so, right? And so in the context of the Delta project, the science paper that I mentioned, the various pseudopotential sets improve. But if you do something like lithium, for example, this is a random example, right? And you use a standard pseudopotential that was out there that seemed to be good. Lithium is very sensitive. And it turns out that this is a very soft material and it could get huge errors in lithium pseudopotential. And I wonder how many were out there. And this is all a very detailed and careful benchmarking exercise for any single property. And with all electron codes, you simply don't have that problem, especially if you can do the same thing faster anyway, right? So for the systems that I showed here, I think we're actually pretty fast. So this is not our problem. So we don't have to worry about artifacts like the lithium bulk modulus, which at the time was very wrong and something that was a production pseudopotential that I actually tested to have to benchmark this. And so I think this is the important part. So you have to do a lot more benchmarking. And in fact, I think FHI-aims in theory could be run with pseudopotential, right? It's just that you have to do very, very detailed benchmarking. And so with the all electron approach, we do not have that problem. We can just run, and so we don't have to parameterize anything underneath. And this for me has been a big advantage over the years. We can test.
Okay, thank you.
So then we have another question in the Q&A. So from Sandeep Kumar. So how does the choice of inorganic cation influence the electronic properties and stability of layered hybrid perovskites?
So in the inorganic cation, it depends on which cation, right? So the inorganic cation is in the B side. So for example, the lead will shift around the actual band gap, for instance, if you go from lead to tin or from lead to something else, that changes. It will also affect the stability in that example, because tin is more easily oxidizable, and so the material becomes less stable in air. That's led to tin. And so in many respects, changing the cation, of course, has the appropriate chemical responses, but you want to test them and you want to know about them, and they're all individual. If you take the A side cation, which I think you're not referring to, then of course a lot more is possible because you change the dimensionality of the system. But also the inorganic cation really tunes the energy levels that come from the inorganic and the chemical stability that's associated with the relevant element.
Okay, thanks, Volker. So another question from the chat. So did you tune the exact exchange for the HSE functional, or did you keep it at 25%?
We kept it at 25% here. And the only reason to do so was that we wanted to be able to compare trends between different materials without knowing the outcome at the outset. The tuning of the exact exchange is a thing that one can do if one knows the band gap. But if one does not know the band gap, the fundamental gap in advance, one has to set the exchange somewhere and hope. So it turns out because of excitons in the systems, getting the fundamental gap in the perovskite is not that easy. But we know for phenethyl ammonium lead iodide, for instance, that we're at the lower end of the alpha parameter, the exact exchange parameter that we should be using. We actually undershoot the band gap in this case by 0.6 electron volts. So that's about the largest that I know from databases that have been published. But that's in the range of HSE as it's been published in the literature and its accuracy. And you see that if you go to different materials and you look at the impact of the material, the spread of values that you get out from DFT. The spread is about 0.8 electron volts or so wide that you can expect. So HSE will have trouble getting you much better, and then it becomes very chemical element dependent. And so we wanted something that at least would not introduce arbitrariness into our calculations by having to guess the experimental relevant value before we knew it. Right.
Okay, so there's a couple of questions from Ibrahim, and maybe these will have to be the last ones for the moment in the interest of keeping on time for Marcus's talk, but everybody feel free to ask more questions, and Volker will still be around at the end of the next talk to answer the remaining ones. So yeah, I just read out Ibrahim's first question first. So can you talk about the use of dielectric dependent hybrids for 2D or 3D perovskites?
Yeah, so I cannot say much about dielectric dependent hybrids because we have not tried them. I think the impact for 2D and 3D perovskites would be better, but there, the key is again that the material is inhomogeneous, and you will have to have a degree of approximation in how you treat the organic versus the inorganic part. My personal bet for this, but that's the future, is to do something that's closer to maybe a local hybrid or real GW calculations if we get there. That would be nice, because then I think the screening is captured correctly. But I cannot say anything specific about dielectric dependent hybrids because I haven't tried them. For the energy level alignment, we use direct supercell calculations in what I mentioned. So we had the same components in the supercell, and so we did not need to do any kind of alignment. We have used four-state alignment in the past before, but I believe that you really want to know the interface between the material explicitly if you want to get the alignment absolutely correct. Yeah, but cross-state alignment is something that we've done between different materials. But normally we run on the fact that we can actually put both components into the same supercell and we don't have to align between different calculations.
Okay, thanks, Volker. I guess I can quickly ask Sandeep, because I think this is a yes/no question. Is it possible to compute resonant inelastic X-ray scattering spectra using FHI-aims?
So I think it's not possible at this time. However, there are several people working in the direction of X-ray spectroscopies, and so this could change, right? This is really interesting because we have a number of people who are actually working on X-ray spectroscopies, and so I'll hedge in this case because it could be that this actually becomes possible suddenly. Yeah.
Okay, thanks, Volker. So yeah, the remaining question, and again, if anybody has any further questions to Volker, please ask them in the Q&A, and we'll get to them after Marcus's talk. So now I'll just briefly hand back to Konstantin to introduce Marcus.
Thank you again,
I'll
James.
stop sharing.
And thank you, Volker, again, also for the nice
And thank you to
Q&A session.
everybody for the questions. Thank you very much. Much appreciated.